Hi guys, this is the model problem for your pre-work for tomorrow's lesson on implicit differentiation. This has been a big struggle for a lot of us. I'm on page 20 of your packet. If you're not there, pause the video, go grab your packet and start again when you're ready. I'm going to be checking your notes tomorrow for completion, so make sure that you're taking accurate notes and writing down what I'm writing. We're going to run through this model problem in the next 10 or so minutes and get you guys all set up for tomorrow's class. So I've got here the implicitly defined curve xy squared minus x cubed y equal to 6, and my instruction is to find dy dx. So we used to do these a lot in the fall semester, and it seems like we've forgotten a lot of how this skill works. I've got an equation that's implicit because x's and y's are all kind of jumbled together, but that's still an original function, or curve, I guess I should say, and I want to try and find its derivative. So I'm going to be using my derivative rules like product rule, chain rule, quotient rule, power rule, all that good stuff. But the task or the challenge is that the x's and y's are all jumbled up. So specifically, when I read this and really start internalizing what's been given, I recognize that I've got an x times y squared minus an x cubed times y equal to 6. And as soon as I put that implied multiplication in here, what I'm noticing is that I'm going to have product rules on both of these terms, and fig plus gif is going to really be helping me out in order to be successful here. So what I'm going to do is try and group this. I'll do a product rule on this first product, and then I'll do the second one here in a minute. So I'm going to identify then the x. The first term of the product is my f. The y squared is my g. So if I try to just run through this, the first thing I need in order to use this product rule is the derivative of f. The derivative of my f is just a 1 because x's derivative is 1. I'm supposed to just multiply that by g, exactly like I see it. And then add to that, here's the tricky part, the derivative of g times f. The derivative of g, your instinct is probably telling you that the derivative of g is 2y. And that's not untrue. Y squared definitely goes to a 2y. But because my x's and my y's are mixed together, I have to remember that the derivative of y is dy dx, and I attach that to any y derivative throughout this process. So that entire term right there, let me just annotate a little bit more. This whole piece is the g prime part of my derivative. And I still need to multiply that by f, which is x. I'm going to switch colors now because what I want to do is subtract then the derivative of the x cubed times y, still utilizing the same product rule. I'm going to just do it on the second product that I see. So if I run through this again, I've got f prime being requested first, that's 3x squared, times g, which is y, plus, here's the tricky part, the derivative of y is going to be g prime. So g prime is the derivative of y, which your instinct might tell you is a 1. But because that's a y variable, I add in my dy dx times f, which is x cubed. And maybe it might be helpful for all of us if we go in and just annotate these product rules a little bit more. This 1 at the very beginning was my f prime, and the y squared was my g. Already annotated the g prime, but let's not forget this little x at the end was my f. So I've got my fig plus gif for the first one, all anchored up there. And then on my black terms back here, I've got my f prime and my g plus my g prime and my f, another fig plus gif. And what I need to be extra careful about is that I group this second one in black because of the subtraction that I see in the middle of the two terms. And let's not forget that that 6 has a derivative of 0. So I'm well on my way now to being able to find my dy dx, but I've got a lot of stuff that could be cleaned up, okay? I'm going to do some simplification here, see if we can get on board with this. 1 times y squared, that's y squared. 2y dy dx, I'll write that as, times that x, is 2xy dy dx. distributing this negative, minus 3x squared y minus 1x cubed dy dx is equal to 0. You'll notice I have 4 distinct terms here, and 2 of them have dy dx's in them. I'm going to keep these 2 where they're at. I'm going to move the other stuff to the other side. 2xy dy dx, stay in put, minus x cubed dy dx, stay in put, equals 2. Let's make that negative 3x squared y positive when I send it over here, and that y squared at the very front, that'll be negative when I move it to the other side. Excuse me. All right, since both of these have dy dx's, I can factor out the dy dx. And I'm left with a 2xy minus x cubed equal to a 3x squared y minus y squared. And if I come over here, only thing left to do is a quick division. And I can finally arrive at my answer that dy dx is just 3x squared y minus y squared all over 2xy minus x cubed. All right, so I'm going to go through some really common follow-up questions now to make sure that we're prepared for everything else that could be thrown our way. The first thing that we're being asked is to write the equation of a tangent line at the point 1, 3. So as you know, equations of tangent lines follow this format. And what we always need in these situations is a point and a slope. The great news about this problem is that the point is handed to me on a silver platter. I don't need to do anything to find that. It's 1, 3. And then the slope, I remember, is synonymous with a derivative. And in the previous problem, we spent a whole bunch of energy establishing that the derivative of this implicit function is, I forgot a y, 3x squared y minus y squared all over 2xy minus x cubed. Make sure I wrote that down right. I think I did, but you've got yours right up above on your notes. So I'm just recording the derivative that I found up above down here in part A. And if I want a numerical slope for this tangent line, all I need to do is take this equation that represents my derivative. Notice I'm putting a whole bunch of parentheses here, because what I want to do is drop in my x value of 1, here's my x and my y, everywhere I see an x, I think I got them in all the right places, and a y value of 3 everywhere I see a y. And then I can just do some math and generate my slope. So 3 times 1 squared times 3 is 9, minus a 3 squared is also 9, over 2 times 1 times 3, 6, minus 1 in the denominator, that's 0 divided by 5, which still causes a lot of you some grief. 0 over 5 is a big fat 0. So the slope of my line is 0, which means my equation, 0 times x minus 1 plus 3. No need to simplify, we're done. Okay, another really common follow-up is to be asked to determine the concavity of the original curve at a single point, showing all of our work. So concavity, if I'm thinking back to the original relationships that I established back in the beginning of the year, for f to be concave up or concave down, that means f prime, or our derivative, would need to be increasing or decreasing, and f double prime, or double derivative, would need to be positive or negative. Easiest relationship to use here is the one involving sines. So what I'm going to try and do to determine the concavity of the original function is demonstrate the sign of the double derivative so that I can draw that conclusion. So what I know, again, from the previous work that we've done, is that dy over dx is equal to 3x squared y minus y squared divided by 2xy minus x cubed. This is going to be a doozy because this first derivative is in and of itself a quotient. So if I want to find the next derivative, I'm going to have to do fig minus gif over g squared. remembering through this that the top is F and the bottom is G. So the first part of this quotient rule requires me to find the derivative of the numerator over here, which doesn't look horrible, but when I dig into it, the very first term that I need the derivative of is a product. So I'm going to be doing a product rule in the middle of my quotient rule to try and figure out what's going on here. This is going to be a nightmare, so I'm glad we're in this together. Let me start this. The double derivative, there we go, is equal to f prime. All right, fig plus gif, here we go. 3x squared goes to a 6x. G is y. Plus g prime is 1 dy dx. And f, it's 3x squared. That's my first product rule right there. Minus the derivative of y squared is 2y dy dx. I'm going to go ahead and switch colors here because all I've done so far is found this part of it, f prime times g. What I'm going to do now is subtract in parentheses g prime times f, which is going to be the, hold on, I'm not even done yet. Shoot, you guys, let me erase this. I got ahead of myself. What I just found right here was just f prime. I need to multiply that by g, 2xy minus x cubed, the function on the bottom. Now, oh good lord, I'm going to try to find g prime times f, so the derivative of the bottom, which also has a product in it, and I'll multiply that by f in a second. Product rule, derivative of 2x is 2 times g is y, plus the derivative of y is 1 dy dx times f, which is 2x, minus the derivative of x cubed is 3x squared. All of that is g prime. I'm going to run out of room here, but I got to multiply that by f. That's 3x squared y minus y squared. All over the denominator squared. Okay, this is a nightmare, I know, but I still need to utilize my point 1, 3 to be able to determine if the double is in fact positive or negative so that I can answer the question about concavity. The good news is, in the midst of this nasty double derivative, I do see dy dx's a few times here floating around inside of all of this stuff. And what I just uncovered in part A is that dy dx is 0 at 1, 3. So not only am I going to plug in an x value of 1 and a y value of 3, I'm going to plug in a dy dx value of 0 everywhere that I can. And watch this. Okay, I get 6 times 1 times 3. That's 18. Plus 1 times 0 times 3 times 1 times squared, 1 times 1 squared. That goes to 0. Minus 2 times 3 times 0, there's another 0. All that will multiply by 2 times 1 times 3, or 6, minus 1 cubed, so minus 1. Minus, I'm going to keep chugging along, 2 times 3 is 6, plus a big fat 0, because the dy dx shows up there, minus 3 times 1 squared, which is 3, all multiplied by 3 times 1 squared times 3, which is 9, minus 3 squared, that's another 9. How nice. All over 2 times 1 times 3, which is 6, minus 1 squared. All right, I know that's a mess, but I get 18 times 5 up top, minus right over here, let me try and show you where I'm looking. This is just 0, because 9 minus 9 is 0. So what was that? 18 times 5 over 5 squared. Let me try and squeeze this in down here. 18 times 5 over 5 squared. Not sure what that is, but I'm darn sure it's positive because I don't see any negatives. So what is the concavity of my curve? Well, the curve is